So an example of exponential decay is radiocarbon dating. The way that this works is actually really interesting. So there's essentially three types of carbon that get stored in organisms, two of which are stable, one of which is radioactive and decays. And it decays at a rate so that its half-life is 5,730 years. So what that means is that this is a statistical statement now, but whatever amount of carbon you start with, about half of it will be there after 5,730 years. No matter how big of a pile, you can just imagine like a big pile of carbon, which is a nonsense idea. But the point is that half of it would decay after 5,730 years. That's with the error bar of 40 years. So it's the half-life is really 5,730 plus or minus 40 years, but let's just, for simplicity's sake, say 5,730. So two of the isotopes are stable, so you can check how much carbon was in the organism at the time that it died, because it stops, it's just stable. The amount of carbon that was in it when it died just stays there. And then the amount of C14 decays, okay, again, at this rate of having a half-life of 5,730 years. And so what you can do is by comparing those three isotopes, you can determine how old an organism is, which is pretty cool. So this was Nobel Prize winning in the 40s or early 50s. And it's a pretty cool idea, and it's a very effective idea, at least for things in certain ranges. So if you have this is not a good way to tell how old dinosaurs are. You have to come up with different methods because dinosaurs lived too long ago. So there's basically, if you have a half-life of 5,730 years, that means that every time you increase time by 5,730 years, you have half of what's left. So there's basically no C14 left in any dinosaurs at all. So you have to come up with alternative methods there. But anyways, this is a really effective method for dating many things here. So what we're going to do is we're going to look at an example where there's a burial cloth that's supposed to be 2,000 years old. Radiocarbon dating shows that the cloth contains 91.97% of its original C14. C14 is the isotope of carbon that decays. And given that C14 has a half-life of 5,730 years, how old is the cloth? And so we know that the amount of carbon that's going to be there is the amount that we start with times e to the minus kt. What I'm going to do is, this is going to be a slightly different version of before, but I'm going to make k positive, and therefore minus k is negative. And so what we have to do is we have to figure out what's our value of k. And so the only real piece of information that we know is the half-life. We know that after 5,730 years, on the one hand, this is going to be a naught, the original amount, times e to the negative kt, where t is 5,730. On the other hand, this should be half of what we started with, because that's what the half-life is. It's the amount of time that you have to wait for half of that material to decay. And so if we take this equation, so we have 1/2 a naught equals a naught e to the minus 5,730 times k, we can divide both sides by a naught, so that's no big deal. That's why the initial value doesn't actually matter when we're talking about half-life. And then we could solve this equation for k. So take logs, divide by whatever we need to divide by. And it turns out that k is going to be negative natural log of a half over 5,730, which works out to 0.00012 okay, just to stop at a certain point there. So that's our value of k. And therefore, what this means is that our equation, A, is going to be however much we start with, times e to the minus k, which we just said is this crazy number, 0.000120097 t. Okay, so that's the amount, and this is our equation that we're going to work with. And then what we're going to do is we're going to have to solve for t. So we want to find t So the A of t is equal to what was it, 91.97%, so 0.9197 A naught. And that's our goal now. Okay, so we want to find t, so the A of t is this value. And to do that, what we're going to do is we're going to look at the equation 0.9197 A naught equals A naught e to the minus kt, where k again is this crazy number, 0.0012097 t. And to do that, this is again just a straightforward algebra problem. Divide both sides by A naught, take natural logs of both sides, divide by whatever we need, and it turns out that t is going to be the natural log of 0.9197 divided by minus k. So negative 0.00012097, and that works out to 691.98 years. So most likely that cloth that's supposed to be 2,000 years old is only a little less than 700 years old. Okay, so we can conclude pretty strongly that that cloth is not 2,000 years old.